Thank you very much for the kind introduction and good morning to everyone. So as Carsten has already pointed out, I'd like to talk to you about the next hour or so about spectroscopic benchmark data sets for molecules. And I will be mostly, I should maybe switch on my, now is it on? Yeah, okay. Do you hear me now?
I can do that.
Can you? Okay. Okay, is it now better? Okay. So, as I just said, but only a lower part of the audience heard it, I would like to talk about spectroscopic benchmark. I had the same problem, data sets for molecules. I didn't come up with the title, actually, I think Igor did. Yeah. So, and I will mainly going to talk about density functional theory and also some beyond DFT, which will mainly be GW calculations. And I would like to talk to you about whether, and if yes, how well you can calculate ionization potentials and electron affinities of molecules with DFT or with GW, right? And before I start this discussion, I first want to get one big elephant out of the room, because every time you talk about spectroscopic calculations for molecules with DFT, you encounter the same problem. You talk about a band gap, and everybody talks about a different band gap. Okay, so let me talk about what DFT should do right. And I call it the band gap dilemma. Okay, so first of all, there's an optical band gap that you measure in an optical experiment. It's the difference between the S0 and the S1 state. It's the optical excitation energy. This is something different than what I call the fundamental band gap, which is the difference between the molecule's ionization potential and its electron affinity, where the ionization potential is the energy that it takes to take out an electron and put it into the vacuum, and the electron affinity is the energy that you gain by taking this electron and bringing it into the molecule. Okay? The difference between these two gaps is the exciton binding energy. It's an electron-hole interaction. And for molecules, it's typically some tenth of an eV, but it can be even larger than 1 eV, right? So if you calculate some band gap, you want to make sure what is the actual band gap that has been measured. The problem within DFT is that we tend to do a DFT calculation using some functional, and then we get HOMO-LUMO energies, and then people try to relate those HOMO-LUMO energies to any of these gaps. Now, assume we had the exact functional, okay? And we would calculate HOMO-LUMO energies, a HOMO-LUMO gap in Kohn-Sham theory. It will not equal either of the two. It will not equal the fundamental band gap, and it will not equal the optical band gap. Okay? The difference between the exact Kohn-Sham band gap, so the HOMO-LUMO gap in Kohn-Sham theory, is to the fundamental gap is called the derivative discontinuity. It's just there, and it can be 1 eV. Sometimes it's less, sometimes it's more, but it's not the same thing. Okay? And most of all, it doesn't have anything to do with the optical gap. Okay? If you want an optical gap, you have to do a TD-DFT calculation. Sometimes the derivative discontinuity and the exciton binding energy, if you're lucky, are, well, on the same order of magnitude, and then you find a HOMO-LUMO gap that equals an optical band gap. Especially for B3-lip and some organic molecules, this is often the case, and this is why people do this all the time. But please don't do it. Don't calculate a HOMO-LUMO gap and compare it to an optical gap. It's two completely different and unrelated things. Okay? Don't do it. So that's the first thing. The second thing that you have to realize is that when you go from a semi-local DFT functional to a hybrid functional, you're using two different theories. Okay? On the one hand, you do Kohn-Sham theory for semi-local functionals. And if you use a hybrid functional, most of the time, you do generalized Kohn-Sham theory. Why does that make a difference? It makes a huge difference for the orbital eigenvalues. Okay? So if this is a generalized Kohn-Sham eigenvalue, it equals the Kohn-Sham eigenvalue plus the amount of Hartree-Fock exchange that you use in your functional times this property that I call delta x. This property here is the exchange self-energy. It's basically the Hartree-Fock operator minus the exact exchange local potential that you would obtain by an optimized effective potential calculation, for example. Okay? So basically by changing the amount of Hartree-Fock exchange in your functional, you change the meaning of the eigenvalues. Right? Even if you had the exact functional, just by changing between local and a non-local exchange, so between local Kohn-Sham exchange and Hartree-Fock-like exchange, you change all eigenvalues. Right? The density doesn't change, the energy doesn't change because all these calculations are exact, but all your eigenvalues change except one. And that is the HOMO. And I will talk about that in a second. Now, let's see what happens if you have a molecule with some ionization potential, some electron affinity, and you do 3 different types of calculations. You do a Kohn-Sham calculation, no Hartree-Fock exchange, using the exact functional. I give you that. Okay? You do a Hartree-Fock Kohn-Sham calculation. That is a Kohn-Sham calculation where the exchange is treated non-locally in a Hartree-Fock-like manner. So you take 100% Hartree-Fock exchange, and the correlation is treated in a Kohn-Sham manner, but you still have the exact correlation functional, so this calculation is exact. It gives you the same density and the same energy. It's exact. Okay? And then you do a generalized Kohn-Sham calculation where the amount of Hartree-Fock exchange is something between 0 and 100%. Still exact. All 3 give you the same density, the same energy. What will happen to the eigenvalues? The HOMO eigenvalue will be the same in all 3 approaches. This is called the IP theorem. It's a very fundamental theorem in density functional theory. Why is that? Because it is strictly related to the density. The density falls off exponentially, where in the exponent you basically have the HOMO eigenvalue. If you have a single particle approach, like Kohn-Sham or generalized Kohn-Sham DFT, your density is a sum of all orbital densities, right? And all those orbital densities will fall off with their eigenvalue. So the density itself will fall off with the highest occupied eigenvalue, because when you go far outside, it will be the only density left. So this relates the HOMO eigenvalue to the ionization potential strictly via the density. And the density is the only thing that is the same in all 3, and the energy. Okay? So that is why the HOMO eigenvalue will be the same. But the LUMO eigenvalue will be very different. So the LUMO eigenvalue in this Kohn-Sham and the Hartree-Fock Kohn-Sham will be very different. In the Kohn-Sham it will be smaller than the electron affinity. In the Hartree-Fock Kohn-Sham it will be larger. Meaning that if you do a generalized Kohn-Sham theory, you get something in between. And there will be, for some molecules, some amount of Hartree-Fock exchange for which actually your HOMO-LUMO gap in generalized Kohn-Sham equals the fundamental band gap for some amount of Hartree-Fock exchange. Okay? But this doesn't make your calculation any more correct, right? All of these functionals, all of them are exact. They give you the exact density. Just the meaning of eigenvalues changes. Okay? So these 2, if you don't take anything else from these talk, take these 2 slides, because they're very important to understand what you're doing when you're running a DFT calculation. Okay, so my talk is going to be divided into 2 parts, where in part 1 I'm going to talk about theoretical benchmarks, meaning I compare DFT and GW results to a theoretical benchmark. Then, of course, eventually you want to compare to experiment. So in part 2, I want to talk about a comparison to experiment, which experiments we can compare best to, and what we need to take into account when going from a theoretical to an experimental benchmark data set. And we had quite a few of that already this morning in the first talk. But I'm going to focus on molecules in my talk entirely. Okay. So this is the data set that I'm going to talk about mainly throughout the talk. It's 24 organic acceptor molecules. These are acceptor molecules because we want molecules for which the electron affinity is positive, meaning that the molecules actually want to take an electron. Okay? This is a study that has been published in 4 back-to-back articles in late 2016, and it includes DFT, it includes all sorts of GW, and it also includes electron propagator methods. We choose these systems because, first of all, they are practically used organic semiconductor acceptor molecules, and second, because they're small enough that we can do a good benchmark for it. And what is a good benchmark? It's basis set extrapolated coupled cluster calculations. We heard about coupled cluster this morning. I just want to say 2 things. The first thing is there's another rather recent benchmark that focuses on GW calculations. It's the GW100 benchmark. So this is only GW, but it's a very detailed calculation for more molecules. And they also compare FHIMs to many other GW codes, which you might find interesting if you are interested in doing GW calculations in different codes. So this is in this paper. You might want to read it, or maybe Patrick, when he gives his talk next week, will talk about this as well. So just one thing about the benchmark. Okay, so we use basis set extrapolated coupled cluster. What is that? We heard about MP2 calculations and we heard about coupled cluster calculations this morning. We also heard that coupled cluster calculations are very, very sensitive on the basis set. So you have a very slow convergence with basis set. We want to have basis set extrapolated. So we want to go to the basis set limit of coupled cluster. The way you do this is you play a trick. What you see here on the left is IPs and on the right is electron affinities. What you see on the top is the difference between an MP2 IP and a coupled cluster IP as a function of the basis set size. And on the bottom, you see the MP2 ionization potential as it converges. So that's the difference to the most accurate calculation. The point is that this is an order of magnitude smaller than this, meaning that the difference between an MP2 and a coupled cluster calculation is an order of magnitude smaller than so the error that you make here, then the error you make in the basis set extrapolation. Meaning we play the trick that we extrapolate this difference, and we can do this for smaller basis sets, and then we extrapolate the MP2, there we can go to much larger basis sets, and then we combine the two, and we get a basis set extrapolated coupled cluster result. Okay? So that's the basic idea. So we are doing basically coupled cluster at the complete basis set limit. The largest errors that you obtain by doing the basis set extrapolation, you get good errors. The largest errors that we obtain are 0.03 eV. This is for the molecule where the basis set extrapolation worked worst. Okay, so this gives you a feeling for how accurate these calculations are. Okay, now let's compare DFT functionals. We did 30 different DFT functionals. And this is a lot of data, so I want to show it in a certain way. What you see here is there are 2 ways you can do the IP calculation or the EA calculation using DFT. One way is you do a delta SCF calculation. So you do the calculation for the neutral, for the cation, for the anion. You take the energy differences. In this way, you get the IPs and EAs. The second thing you can do is you can just do a calculation and then take the HOMO-LUMO eigenvalue and compare it. Okay? So what is plotted here is here's the delta SCF minus the coupled cluster benchmark, and here's the negative HOMO minus the coupled cluster benchmark. So if something is on this line, it means the delta SCF gives a good result compared to the coupled cluster. If it's on this line, it means the HOMO gives a good result compared to the coupled cluster. If it's on this line, it means that the functional is consistent in the sense that its HOMO equals its delta SCF result. Okay? Of course, the exact functional would give us only results at the center where everything is 0. Okay? So now we start with semi-local functionals. This is basically the result that you get from all semi-local functionals that we have tested. And what you see is that generally the HOMO is much too small. You sometimes get the delta SCF right by coincidence, but there's not one functional that works significantly better than the others. It's a pretty large spread. You can't really say, okay, choose this or that semi-local functionals. The HOMO eigenvalues are all too small, and delta SCF, sometimes you're lucky. Okay? The same is pretty much true for the electron affinities. Okay? So probably not a good idea to use semi-local functionals. So let's do it more accurately. Let's do hybrid functionals. And I start with global hybrid functionals where the amount of Hartree-Fock exchange is globally the same everywhere. So you mix in 10, 20, or whatever amount of Hartree-Fock exchange. These are the ionization potentials, and these are the electron affinities. And you see there's clustering of results. And basically, if you look closer, you see there's a trend with the amount of Hartree-Fock exchange that you use. So for the ionization potentials, the trend is rather clear. Basically, your HOMO eigenvalue goes down, so the negative HOMO eigenvalue goes up as soon as you include more Hartree-Fock exchange. Okay? For the electron affinities, it's a much more complicated behavior, but you can actually understand that. Why is that? Your whole eigenvalue spectrum, including the HOMO, gets shifted downwards as you include more Hartree-Fock exchange, and at the same time, your HOMO-LUMO gap opens up because of what I just said. You include this, you go from cone-sham to generalized cone-sham, and the meaning of your LUMO eigenvalue changes as you include more and more Hartree-Fock exchange. So you have these two trends. The entire eigenvalue spectrum goes down, but the gap opens up, and therefore you get this type of behavior here as you include more and more Hartree-Fock exchange. Now, what is really interesting is that none of the global hybrid functionals, none of the standard global hybrid functionals gives you really good HOMO eigenvalues. Okay? Now, you could say, what is the optimal amount of Hartree-Fock exchange that I would need? And this is shown in these two plots for IPs and EAs. Again, we just take one functional, we change the amount of Hartree-Fock exchange, and then ask for which amount of Hartree-Fock exchange do we get the perfect answer, or the best answer compared to the coupled cluster. And we do this for the HOMO and for the delta SCF. And you see for the HOMO, so this is the number of molecules for which this amount of Hartree-Fock exchange is the best. So what you basically see is that for the molecules, you typically need between 70 or 80% of Hartree-Fock exchange to get the IPs right, and well, maybe a little bit more for the electron affinities if you want to interpret the LUMO. But for the delta SCF, there's really no trend at all. You can't really say, okay, B through lib is perfect, it has 28% of Hartree-Fock exchange, or whatever, right? So the amount of Hartree-Fock exchange doesn't really influence the delta SCF, where it's for the HOMO and LUMO, it's more decisive. Now, next step, let's go to range-separated hybrid functionals. And first thing you realize, there are a lot of them that actually perform really well. The second thing you realize, there's a clustering of results. These here are basically HSE, and adapted version of HSE where you have some mid-range exchange. So HSE, as most of you know, has Hartree-Fock exchange in the short range, for short-range electron-electron interactions, and semi-local exchange for long-range electron-electron interactions. Okay? So they are not really doing well for this case. This one is CAM-B through lib. CAM-B through lib has some short-range and some long-range exchange, but it has some percentage for short range and some percentage for long range, but no full long range exchange. Finally, these are all functionals that have full Hartree-Fock exchange for long range electron-electron interactions, and they work best. Okay? So quite obviously, Hartree-Fock exchange matters, and it depends on how you mix the Hartree-Fock exchange. That seems really to be important. Can we understand this? And in order to explain to you why that is the case, I want to make you familiar with my favorite example that shows what's going wrong with DFT. I take 3 helium atoms, okay? Just 3 helium atoms at a certain distance. and I take out one electron. So I create a hole. And then I start increasing the distance r between those 3 helium atoms. Okay? So stretch it apart. And then I want to know what happens to the hole. So I basically look at the charge sitting on the central helium atom. It's a symmetric system, so you would expect the charge would localize at some point on the central helium atom. Okay? I like the system because I can do a full CI calculation for this. It's a rather small system. I know the exact answer. Okay, so this is what happens. The red curve is the full CI. This is the charge on the central helium as a function of distance. And you see it slowly but gradually localizes on the central helium atom. If you do a Hartree-Fock calculation, it localizes very quickly. Just wants to localize and it stays there. If you do a DFT calculation with a standard functional, and it doesn't really matter which one you take, the charge forever stays completely delocalized, and you have 1/3 of a charge on each of the 3 helium atoms. Okay? That is what happens in DFT. Now, how can we understand that? Let's just sit on one helium atom and change the number of electrons on this helium atom. Okay, one helium atom in an empty universe. We know what the total energy should do. This is an old paper by Purdue and co-workers from 1982, very famous. Most of you may know it. So you can show that the exact energy of this helium atom, where you change the fractional number of electrons, is a straight line with kinks at integer occupations. So here, the slope of the line changes. So you have a discontinuity in the slope or in the derivative, which is exactly the derivative discontinuity that I was talking about. It is related to a jump in the exchange correlation potential. That is what the exact functional must do when you cross an integer particle number. The potential jumps and the total energy changes. The slope of the total energy changes. Now what does Hartree-Fock do? Hartree-Fock does this type of thing. Okay? So the discontinuity is too large. Remember this plot where I showed what the Cone-Cham-Hartree-Fock gap is? It's too large. That is the exchange discontinuity that I mix in when I do a hybrid functional calculation. Okay? This is exactly this. This gap is too large, the kink is too large, and Hartree-Fock bends in order to account for that problem. But if you now go to a situation with half of an electron, let's say this situation is spuriously destabilized in Hartree-Fock. So Hartree-Fock really doesn't like situations with fractional electron numbers on certain subunits of your system. That's why it tries to localize this charge on the helium as quickly as possible. Okay? If you do a DFT calculation, this is what happens. Remember the Cone-Cham DFT result? The Cone-Cham gap was smaller than the fundamental band gap. There was no inclusion of the derivative discontinuity. There's no or a too small derivative discontinuity. And situations with fractional electron numbers are spuriously stabilized, meaning that these functionals really like situations with fractional electrons, which means that the electron in this case, or hole in this case, tries to stay delocalized as often as possible. Now this is a very small model system, but you have that in every DFT calculation that you will ever run, okay, with these types of functionals. You put a molecule on top of a surface, you put two molecules together, you do whatever you want. DFT, these functionals will always try to delocalize charges if it is somehow possible because of this situation. Okay? This is called the delocalization error, and the error of Hartree-Fock is the localization error. Now, why can now these long-range corrected hybrid functionals approach this problem? And why are their IPs and EAs better? First of all, you have to realize that there's Janak's theorem that tells you that the derivative of the energy with respect to the fractional particle number is the HOMO energy, meaning the slopes of these lines here are the IPs. okay, telling you that the IPs of these functionals here are too small and the IP of Hartree-Fock is too large. That is just Yannick's theorem. So we would need a functional that would give us a straight line behavior, then we would also get good values for IPs. Okay? So why do these long-range directed hybrid functionals obviously do that? Well, because they do exactly what we need. They separate the interactions into short-range and long-range interactions via an error function, and then you take semi-local or hybrid DFT in the short range and full Hartree-Fock exchange in the long range. So in other words, in the short range, for short range interactions, you take something that has a delocalization error, so you prevent charges from localizing too much. And in the long range, you have something that has a localization error, so you prevent charges from delocalizing too much. And that is exactly what these functionals do. And then the only open question is, what is short range and long range? And this depends on your system. Obviously, for different types of systems, short range and long range will be very different. So how do we determine this range separation parameter? And well, one of the ideas put forward by Kronig and Baer a few years ago and followed by a lot of groups is to just say, well, we know what the correct answer should be. The correct answer is the slope of the line. So the HOMO eigenvalue should equal the energy difference between the neutral and the cation. Then this line shows into the right direction, and we get hopefully a straight line. And that you can do. You can do a DFT calculation for neutral, a DFT calculation for the cation, calculate the HOMO eigenvalue, and if the two agree, then you have the correct range separation parameter for your system. And that you have to do for each system. Okay? And if you do that, and what is plotted here is the difference between the straight line and the actual energy curve is a straight line. So in Hartree-Fock, you have a localization error. In PBE, you have a delocalization error. If you do an IP-tuned long-range corrected hybrid functional, it gives you a straight line. And not only when you take out an electron from the HOMO, but also if you put an electron into the LUMO. It's more or less a straight line. Okay? So it's a straight line, and therefore it gives you good results for IPs and EAs because they are related via Yannick's theorem. Okay, so just quickly going back to my example, because people always ask me, so how do the long-range directed hybrid functionals perform for this problem? This is what they do. So they start out on the full CI curve and then they break off. And this is really disappointing, but then you do quantum chemical calculations, and you see even a couple cluster result, which is here. So the perturbative triple does something weird. The CCSD is pretty much on top of the, well, rather close to the long-range corrected hybrid functional, meaning this here is a multi-reference problem, and you don't get that right in DFT. So what these functionals do is they correct the delocalization error of DFT. They do not go beyond that. They do not include multi-reference situations. Okay? Also something you have to take into account that sometimes these charge transfer problems are multi-reference problems. Okay, so what happens if we do the IP tuning? If we do the IP tuning, we're on this line for the IPs because that is exactly what we put in to determine the range separation parameter. And then if you do that, so sometimes this doesn't really work. Sometimes we don't find a range separation parameter that gives us exactly delta SCF equals IP. And then we can be a little bit off. But the same thing also gives us good results for electron affinities. Okay. So going back to the benchmark, we see that if we do delta SCF calculations for PBE, then for PBE 0, and then long-range corrected omega PBE, all of them based on the same functional structure, just different mixing of Hartree-Fock exchange. And here doing the IP tuning, we reduce the error. And this is compared to the delta SCF, which generally is much better than interpreting HOMO and LUMO eigenvalues. Okay? So but you might still say, okay, this is really strange because, well, okay, I do the IP tuning, but I don't gain that much, do I? The main thing that you gain is these are delta SCF calculations and these are HOMO-LUMO eigenvalues. So that is really important. We now have a functional that not only gives us in delta SCF good IPs and EAs, but also has good HOMO-LUMO eigenvalues. Now I want to convince you that this is really important by showing you an example. And this is the example of TCNQ and TTF. These are the HOMO-LUMO eigenvalues of TCNQ and TTF calculated with some benchmark that we believe. Okay, so the HOMO of TTF is well below the LUMO of TCNQ. If you put one TTF and one TCNQ together, there's no charge transfer between the two, right? Clearly separated. Now you do a PBE calculation or a PBE hybrid calculation. This is what the situation looks like. You have the HOMO of TTF above the LUMO of TCNQ, even for the hybrid functional, and you end up with a charge transfer between the two of a quarter of an electron, which shouldn't be there, quite frankly. It's spurious. It's because you have a functional that does not give you good results for LUMO eigenvalues. And that is why we need functionals that are not only in delta SCF, but also for the HOMO-LUMO eigenvalues give us good results, to avoid exactly these kind of situations. Okay. Now, this was about DFT. Now I want to switch gears a little bit and talk about GW. But I will make use of what I just told you also in this discussion. So I'm not going to give a very deep introduction into GW because you will hear talks about that later during this workshop. Just the very brief introduction. You have an electron. Now you have this creates a polarization around it in some material. And this combination of electron and its polarization cloud is our quasi-particle. And then we have these quasi-particles interact. This interaction is not full Coulomb interaction. It's a screened Coulomb interaction called omega. And this is many particle theory that you can solve. You obtain the Dyson equation that looks like this with the exchange correlation self-energy. And the self-energy can be written in a certain way. And then you need the Green's function. But for the self-energy, you can't calculate the full thing. You make an approximation. And you just take this first order. It's Green's function G times screened interaction W. And that is why the thing is called GW. It's a GW approximation to this many particle perturbation theory. And then you have corrections to it. What you obtain then are the quasi-particle energies from the Dyson equation. Most of the time, these GW calculations are done non-self-consistently, meaning you do a DFT or a Hartree-Fock calculation. You take the orbitals and eigenvalues from this DFT calculation. You plug it into the Green's function here. So these are the orbitals and eigenvalues that you plug in. You calculate once the screening, and you predict once the quasi-particle eigenvalues from this. Okay? So you end up with a correction of your Cohen-Sham or generalized Cohen-Sham eigenvalues towards the GW ones, a one-step correction. Now, what is the problem? If I use a DFT functional, semi-local DFT functional, I just said the gap is smaller than the fundamental gap, meaning the screening will be too large, right? So my correction will be wrong. That is the first thing. The second thing is my HOMO eigenvalue is not really good. Now, this is a perturbation theory, meaning I should start from a good initial HOMO eigenvalue. Okay? So this leads to the problem that if you do a GW calculation non-self-consistently, you can get all sorts of problems, and you get errors. And we checked in our benchmark how large those errors are depending on the starting point. This just is a different study that we did before that. For the different DNA, RNA nucleobases, where you nicely see what's the problem. So here in the center, you have experimental data for the IPs. You have COS-PT2 reference data that is, well, somehow okay compared to experiment. I will talk about that later. And then you have a GW calculation once on top of Hartree-Fock and another GW calculation once on top of PBE. And the difference between the two is 1 eV. So you get this range of results from GW just by changing the starting point. And this is, well, this is the underscreening of Hartree-Fock. The band gap is too large, screening is too small. the overscreening of PBE, bandgap is too small, screening is too large. But none of the two is really correct, right? None of the two really gives you a good comparison to experiment. You can see what the problem is. If you do a self-consistency in the eigenvalues, then you get a better bandgap, you get a better screening, and your result is okay. Or if you use a functional that actually gives you good homo-luma eigenvalues, like a long-range corrected hybrid functional, if you use that as a starting point, you're pretty much on top of the eigenvalue self-consistent GW, but at the cost of a DFT starting point, so one-step GW correction. How does this perform for the benchmark? You've seen these results before. Now I added the GW results. This is GW on top of a PBE, and it's so much worse than if you just do a delta SCF PBE. Okay? So this is how bad it is. For molecules, it's really not a good idea to do a GW on top of PBE. And for many years, people have benchmarked their DFT results, like the long-range corrected hybrids ones, against these results, which also turns out to be not a good idea. Now, you can make it better by using a hybrid functional because of the fact that I said you increase the band gap by including some Hartree-Fock exchange. Screening gets a little better. Hartree-Fock is even better than the semi-local functional for the molecules at least. Self-consistent GW, again, is not really a good idea. If you use a GW on top of the functional that should work, it gives you small errors on the order of 0.0 EV, which in the entire benchmark that I introduced earlier was the best result for IPs, EAs, and gaps. So non-self-consistent GW on top of a functional that should actually work as a starting point works. That's the positive side of things. This is a very busy graph. This should just show you what's exactly going wrong. So you basically see here's ionization potentials, electron affinities, and you see the number of molecules for which the error is how large. So basically you see if you just go to GW based on PBE, you see the IPs are too large, are too small, the EAs are too large, which meaning the band gap is too small. Right? You get systematic errors. But if you do a good starting point, you get rather small deviations. You get for pretty much the worst results are 0.3 EV difference to the reference data. Another way to look at what's going wrong with the non-self-consistent GW is, again, to talk about this straight line behavior. So you've seen these results already. The Hartree-Fock has this localization error. The PBE has the delocalization error, and you can connect it via Janek's theorem. So Janek's theorem tells us that the eigenvalues are the slopes of these lines, and if you take the, so this is the neutral system. If you take the IP of the neutral system, this is the PBE eigenvalue, and this is the Hartree-Fock eigenvalue. If you take the LUMO eigenvalue of the cation, this is for PBE and this is for Hartree-Fock. So you see this is Janek's theorem tested. It's actually true. But why do I say that? I say that because this way you can also test what GW does. Does GW also have a problem with localization error? Because we can calculate the IP and EA for neutral and cation with TW, and those are these lines here. So the blue line is the TW on top of PBE, and you see it has a small delocalization error. TW on top of Hartree-Fock has this weird thing that here it goes in this direction and here it goes in this direction. Meaning that GW also has a localization, delocalization error. This can lead to different ways of trying to find an optimal starting point for GW. So you can ask the question, what is the optimal starting point for a non-self-consistent GW calculation? The first idea is to, as I said, you IP tune the amount of Hartree-Fock exchange in the starting point and then do the GW correction. I already said this leads to pretty good results. The second idea put forward in this paper is you minimize this deviation from straight line after the GW correction. And you choose the amount of Hartree-Fock exchange in the starting point so that after the GW correction, you get a straight line. Okay? The third suggestion is a little bit older from this paper, where you basically say, I don't care about straight line, I just want consistency. It's a perturbation theory, so it should be consistent. The correction should be small, meaning I just look at the HOMO eigenvalue, and then the correction of the HOMO eigenvalue should be 0, meaning my DFT IP should be equal to the GW IP. So I adapt the amount of Hartree-Fock exchange in this calculation. So why do we want to compare these three different results? Because there's an interesting aspect about this non-empirical tuning of Hartree-Fock exchange. And this happens when you look at systems of varying size. So this is IP tuning, USLE tuning, and GW tuning. So let's look at polyenes. We can calculate the localization delocalization error. Here is again the deviation from the straight line, and here are the full energy curves. This is for 4 double bonds in an oligomer with 4 double bonds. Now we increase the chain length, okay? And the delocalization error becomes smaller. We go to 16 double bonds, and again it becomes smaller. So this deviation from straight line error vanishes as we increase the system size. What's going on is we have the delocalization error. Therefore, charges are completely spread out everywhere. So if we take out a charge, it's immediately spread over the entire chain, meaning at each part of the chain we only take out a little tiny fraction of an electron, meaning we're always in this initial slope region of the deviation from straight line. Meaning, if we have an infinite chain, there will be no deviation from straight line, even with the worst functional. Meaning that this IP tuning idea loses more and more of its credibility the longer the chain is, right? Because we don't know anymore what the IP tuning actually does. So we wanted to look at it. How does it actually work? Again, theoretical reference. We use coupled cluster results for reference up to 22 double bonds in the chain. These are the coupled cluster IPs. Then we do the IP tuning for the different chain length, and we see it's okay for smaller chains, and it becomes increasingly worse for longer chains. This is exactly this problem. IP tuning becomes less and less meaningful in a sense. So we said, okay, let's try these tuning methods. Let's do a GW on top of these DFT eigenvalues, and actually they are perfect for all chain lengths that we saw. As soon as we do the GW, they are really good. If you do the DSLE tuning, so you ask the straight line condition after the GW correction, the results get worse and worse the longer the chain gets. And the amount of Hartree-Fock exchange that you need in the starting point is also getting less and less. And in general, it's much smaller than for the IP tuning. If you use the GW tuning, the one where you ask your IP to be the same in the DFT starting point and in the GW, the amount of Hartree-Fock exchange stays the same, but still the results get worse. So somehow this combination of IP tuning and GW works really nicely, even for this challenging case of you increase the system size. Okay. What you see here is that this is the deviation from straight line. You basically see that if you have a delocalization error, like here in the PBE, this gets smaller and smaller. This is what I just said. You increase the size of the chain. The deviation from straight line gets smaller and smaller. If you have a localization error like in Hartree-Fock, it doesn't change at all because your charge is localized. At a certain point, it doesn't realize anymore whether you make the chain longer or not, right? So it doesn't change anymore. Okay, so in the last few minutes, I want to quickly talk about comparison to experiment. Because so far, I only compared to theory, and then if I talk in front of experimentalists, they say, okay, you're comparing one theory to the other. What should I believe? Okay. I just want to remind you of this plot where I had experimental results, and the results were somehow deviating from these experimental results. But what's the problem here? As we heard this morning, of course, if you compare to experiment, you have to make sure what experiment am I comparing to, what is the error bar on this experiment, how has it been done. You have to take into account 0-point motion, you have to take into account temperature, you have to take into account vibrations. Okay? So let's do this. The best thing we can compare to, if you were interested in IPs and EAs, are gas phase phototron spectra with the best resolution that we get. So we search for really well-resoluted phototron spectra in gas phase, because that's how our calculations are done in gas phase. Okay? Then we did a Frank-Conton analysis. So basically, we calculated the vertical IPs and EAs with the different methods. We needed the ground state geometries, we needed the vibrational frequencies. Then these vertical IPs, these are the ones that we calculate in TW. But this is not the 0, peak that you measure in experiment. The 0, peak also takes into account the 0-point vibrational corrections in the ground state, in the neutral and in the cation. And it also takes into account the Frank-Conton factors. Okay? So you need a full Frank-Conton analysis, you need 0-point vibrations, and you need temperature. So just very quickly how this is done. So you calculate the intensity. It comes from the Frank-Conton factors. Frank-Conton factors are basically Laguerre polynomials. You need the Huang-Gris factor, which takes into account the change in the geometry, which you get from the vibrational analysis if you want. You need the relaxation energy. What does the relaxation, so how does the molecule relax when you take out an electron or put in an electron? And you need the vertical IPs and the 0-point vibrations. Now we put all this, so we put all this together, and this is one of the DNA RNA nucleobases, thymine. This is the not very well resoluted spectrum, and this is what you get from this analysis. This is what you would get if you use different GW starting points. So this is the best starting point that we had, GW on top of the long-range corrected hybrid functional. So these others are just to tell you what's the to see how large the error is if you use other GW, not to talk about DFT. Now we can compare maxima, and it's 70 electron volts. But it's pretty okay, I would say, but we want to have better resoluted spectra. So we went to anthracene and anti-CDA. We did the same type of analysis. This is what you get from the GW plus DFT approach. Again, using a decent starting point for GW. This is what you get from using not good starting points for GW. So you see you would not match the spectrum at all. And for anti-CDA, it's pretty much the same thing. So we can really, without any input from experiment, except the temperature and the broadening, because the broadening is given by the experiment, we can predict the experimental spectrum from ab initio. So directly relating to experiment, testing our approaches. And luckily, the thing that worked best for the theoretical benchmark also works best in comparison to experiment if you do everything right. Here errors are 20, 30 millieV. If you go over the test set, mean absolute errors are 50 millieV for the best approach. You can do electron affinities. These are phototron spectra on the N ions in an ion trap. You can calculate that. Here the error bars are even smaller. Again, if you compare maxima, it's smaller than 10 millieV. And again, if you do other GW approaches, you're much worse. And you can calculate error bars, 30 millieV for electron affinities. And if you put that together, you get error bars for fundamental gaps, 80 millieV with the best GW approach. You get, with TW on PBE, you get 0.8, which is pretty close to what we had in the theoretical reference data. So theoretical and experimental reference data are pretty much, give you pretty much the same results if you do everything as you should do it. Take into account things as you should. Just to show you that you can do larger systems as well. This is C60, you get 60 millieV as well. Okay. I think I'm out of time. I just want to mention.
You have like 2-3 minutes.
Okay. Okay.
We want to have questions after.
Yeah, sure. Okay. So then I just want to take these 2 or 3 minutes to tell you that so far I've only talked about IPs and EAs. But the question of sometimes or often you want to predict the entire spectrum. And this is a completely new level. And this is what I want to tell you right now. This is an experiment for phenanthine, this molecule in the data. This is the experimental data, and we fitted it. So we basically took Gaussians, and then we did a machine learning technique to basically find the optimum parameters for these Gaussians to optimally fit the experimental spectrum. And then we take these parameters and put it on top of our calculations to see if we take into account broadenings and so on via this technique. Can we then just visually compare the results, the spectra, to experiment? And then we did all sorts of things. We did several DFT calculations where the HOMO was shifted according to the delta SCF. We call it a potential adjusted approach. We did all sorts of GW, also GW plus SOSX, which is a correction to GW. And we did the long-range corrected hybrids and GW on top of long-range corrected hybrids. And we did all sorts of analysis trying to just take the difference between the optimal fit here and the different spectra. These are these numbers here, the first numbers in these brackets. And basically what you see is that it's a mess, okay? You can't really say this method works nice and this method doesn't. And that's why I say it's a completely new level, okay? So basically, if you do a PBE0 calculation, you get pretty much the same errors as if you do a GW on top of a long-range corrected hybrid. Okay? And this is the same for pretty much all molecules that we tested. So predicting full spectra is really a big challenge. And sometimes, even if you do an easy calculation, it looks okay, but it's really hard to understand what's going on. And this is my last thing that I wanted to talk about. What is sometimes, because comparing full spectra is such a big mess, sometimes what I really need, because I want to compare my theories to experiment, I need an accurate experiment, and I want to know exactly which of these peaks is which orbital. And you can measure that via angular resolved photodetector spectroscopy. This is just an example. And you can show, without going into the detail, that the photo emission intensity is proportional to the Dyson orbital squared. So you basically you can calculate your orbitals, transform them into Fourier space, and then directly compare to experimental data. And this is what you see here. The HOMO-LUMO energy is calculated compared to the experimental data, and you see you can measure Dyson orbitals via this technique. And then you know which orbital is where. And this is just an example for NTCDA, HOMO and HOMO -1. This is the angular resolved photodetector spectrum. This is a poor DFT calculation. And this is a GW calculation. And you see the DFT actually predicts you the wrong HOMO orbital. And you can measure that directly compared to experiment. And this is a really valuable tool if we want to compare our theories to experiment, because we know exactly what's going on there. This is the HOMO predicted by LDA. This is the HOMO predicted by a decent DFT functional. And you can bring it onto an additional level, like if you go into this peak, the second peak of the photodetector spectrum of PDCDA. This is the ARPAS measurement. You can do a principal component analysis and find that it should consist of 4 orbitals, 4 Dyson orbitals. And then you can try to do the calculation, and you do a DFT calculation, and it predicts you this peak consists of 2 orbitals, and they are completely wrong. You do a GW calculation, you get the correct 4 orbitals. They compare rather well to experiment. It's not perfect because this is a gas phase calculation. Now you put it on top of the gold surface, and you get everything right. So again, just to show you, we need good experimental data where we know what's going on, and then we need to do everything right in theory, take into account, in this case, the surface, take into account bending of the molecule and everything. But then we can make things right. But you have to know what you're doing, and you have to know what your DFT is doing. And that is what I hope I could convince you of during this talk. I thank you for your attention. Sorry for speaking maybe 2 minutes too long, and I'm happy to answer questions.